so ladies and gentlemen, let's talk about, first of all, a polynomial. So it's a word you've heard since Algebra 1, but when we talk about a polynomial is a function in the form of a sub n, x to the n plus that, and you have all these x's with exponents in them. Obviously, if they're in standard form, we always write a polynomial in standard form. We take x with the largest exponent, and that comes first. And then all your powers for x go in descending order. So these numbers, these a sub n minus 1, all of these are what we call real numbers, or the coefficients. And again, you're dealing with a real number. So remember what is in front of your x, you've got coefficients. Remember, the domain of your polynomials are always all real numbers. So if you have a polynomial function, the domain is always real numbers. One thing to be a polynomial function, the powers for your variables have to be real, rational, and positive. So in other words, all of your powers for x, they cannot have any fractional exponents. You cannot have any negative exponents in order to be classified as a polynomial function. So for example, and by the way, what makes a rational number? Let's just review that. What is a rational number? Is pi a rational number? No. How come pi isn't a rational number? Because it's a non-ending, non-repeating decimal. All right, so for example, would this first one be considered a polynomial function? Are all my powers positive whole numbers? Yes. So this is a polynomial function. Yeah. The pi, remember, is not an exponent. The pi is a coefficient. So it's okay to have an irrational coefficient. It's not okay to have an irrational power. What about in b? Would this be considered a polynomial function? No. There's two reasons. Give me one reason why this is not a polynomial function. You have a what? Negative exponent, and there's another reason. E. Because E is our other famous irrational number as well. All right, so any questions, first of all, what makes a polynomial function and what doesn't? All right? So now remember, we like to factor polynomial functions. They're pretty easy to solve an equation that way. So then, remember, your solutions are also your x-intercepts. So if you can solve your equation, remember the solutions are also your x-intercepts. You also heard the phrase roots and zeros as well. So again, if you can factor to solve, you can find the x-intercepts. So again, if we can factor and solve for r, then they are called your real solutions, or zeros. We also can find imaginaries, but we're concentrating mainly on real solutions from now on, believe it or not. We really don't work anymore with imaginary numbers. We're going to concentrate mainly on the real solutions. So let's suppose you have a real zero of f. Then remember, we have the different words we use for the solutions. We call it an x-intercept. Root, zero, solution. Remember, all of those words are the same animal. So x-intercept, root, zero, solution, it's all the same thing. Remember what x minus r is called. If r is your zero, remember x minus r is a factor. That's the factor we use to help us solve for r to find the solution. So let's take a look at example 1. So given, they've already done the factoring for us. Find your zeros and the factors. So first of all, tell me about your zeros. What are your zeros going to be? X equals what? Negative 1 and positive 3. So those are your zeros. You just take each factor and set it equal to 0. Now, what are your factors? Your factors are what? X plus 1 and x minus 3. So if I ask you for a factor, remember that's your actual what you've set equal to 0. So notice it's the opposite sign of the 0 inside the parentheses would be x. Yes, Brian? X minus 3 is repeated. I mean, if you listed it twice, I wouldn't mark it wrong, but again, you've only got really two factors there. One just happens to be a repeated factor. Okay? Kind of getting down here, remember, if the same factor, x minus r, occurs more than once, then r is a repeated or multiple 0 of f. So that square that we have for that x plus 3, that's what we call a repeated 0, repeated factor, repeated solution. All right, so if r is a 0 of even, remember we talked about this last year in Algebra 2, or you should have. You use this word multiplicity. Do you remember what that word multiplicity means? Do you remember? Not sound familiar? All the multiplicity, I'm sorry? Exactly. So right here, when you look at this factored form, that square is your multiplicity. That tells you how many times the factor is appearing. So the multiplicity is actually your exponent for the factor. That's what your multiplicity is. So it's your exponent for the factor, in case you forgot what that word means. So there's something significant that happens when you graph with, that 0 with an even multiplicity. What happens is you're not changing side from one side of the x-axis to the other. The graph is just going to touch. Remember that touches and crosses business? It's just going to touch the x-axis at that particular x-intercept. If you have an odd multiplicity, so in other words, the exponent for your factor is an odd number, like it is up here for x plus 1. X plus 1 is actually to the first power. So if that multiplicity is odd, then it will change sign. What that means, it is going to cross over the x-axis. So then the graph is going to cross the x-axis at r. So you look at that power to see graphically what's happening. Is it just going to touch the x, that kind of bounces off the x-axis, or is it actually going to cross over the x-axis? You can tell by the factored form of your polynomial. All right? You also talk about turning points. If you have a polynomial function of degree n, then remember your function will have at most n minus 1 turning points. Remember, it's always 1 less than the degree. So end behavior you guys also studied last year of polynomial functions. For very large numbers as x approaches positive infinity, or very small numbers of x as x approaches negative infinity. The right and left sides behave like the degree of the polynomial. So, your end behavior. So here's a polynomial function where n is even. So we're looking at an even degree polynomial function. Remember, a is the leading coefficient. So if your leading coefficient is positive, then the graph opens up to the right, up to the left. It looks like your parabola function if it's an even degree, remember. So remember, this is where your a is greater than 0, where your leading coefficient is greater than 0. So if your leading coefficient is greater than 0 and it's an even degree polynomial function, both ends are going to go up, whether it's an x squared, x to the 4th, x to the 6th, or an x to the 100th power. You may not know what's happening in between, but you do know that both ends, the end behavior, both ends will be going up. If your leading coefficient is less than 0, what happens is it's a reflection, if you remember. So then both ends are going to go down. So a negative x squared, a negative x to the 4th, and negative x to the 6th, both ends are going to go down. Now, if you have an odd degree polynomial function, like an x to the 3rd, an x to the 5th, and an x to the 7th, if you have a positive leading coefficient, it will look something like that. We may not know what happens in the middle, but we do know what happens on the left, it's going to go down. What happens on the right, it will go up. So the graph will go up to the right and down to the left. Like I showed you that. Again, that's where the leading coefficient is positive. So again, if the leading coefficient is negative, it reverses itself. So it'll go down to the right and up to the left. So to kind of summarize this with a graph, if you have a positive even power polynomial, so your leading coefficient is positive and it's an even degree, you should be familiar with this notation. When you say as x approaches negative infinity, you are looking at the end behavior on what side, the right side or left side? Left. So remember, this is where you're looking on the left. So as x approaches negative infinity, you're looking all the way over here on the left-hand side of the graph. Then we know f of x is referring to your y values. So notice this graph is going up, it's going towards positive infinity. Same thing when you look at x approaches positive infinity. Are we looking on the left or on the right? On the right. And again, it's also going towards positive infinity. If your power is even, but you have a negative leading coefficient, the graph reflects. So again, as x approaches negative infinity, what's happening with the end behavior here? Is it going towards positive or negative infinity? It's going to go towards negative infinity because it's pointing down. As x approaches positive infinity, it's also going towards negative infinity. Okay? So any questions about the leading coefficient and how it affects the end behavior of polynomial functions? Again, if it's an odd power, so again, you have a positive leading coefficient, the graph will look like this. So you tell me, what's happening as x is going to negative infinity? What direction is this pointing when x approaches negative infinity? It's pointing down, so we'd say it's going towards what? Negative infinity. As x approaches positive infinity, what side of the graph are we looking at? We're looking at the right side, and what direction is the right side pointing? It's pointing up, so it's going towards what? Positive infinity. Again, if you have an odd degree polynomial function, but the leading coefficient is negative, it's going to reverse. So again, as x approaches negative infinity, the direction that your graph is pointing up, so it's going towards positive infinity. As x approaches positive infinity, you're looking at the right-hand side, which is pointing down, which is negative infinity. And it sound familiar a little bit? You guys should have done this last year, back in Algebra 2. That you have to know the end behavior of all your different parent functions, which we're going to be reviewing this unit. But again, these are just polynomial functions. So any questions about that? All right, so there's another way that we could state end behavior. So we've been talking, this is where the little bit of new is going to come in with a little bit of old. When we start calculus at the end of the year, we're going to introduce this idea of limits. And actually what you're doing when I ask you about end behaviors, I'm asking you to find a limit. That's what you've been doing. So as x approaches positive or negative infinity, r of x may approach some fixed number, or it may approach positive or negative infinity. All the examples I just gave you, it approached positive or negative infinity. But it may approach a fixed number y equals L, which is a horizontal asymptote. So we say as x approaches positive or negative infinity, three things can happen with your graph. It's either going to point up, which means it's going to infinity. It's pointing down, it's going towards negative infinity. Or it's approaching that horizontal asymptote. So anytime we're talking about the behaviors x approaches positive or negative infinity, only one of three things can happen. And in calculus, we call this idea a limit. So what basically we're doing when they ask to find the limit, as x approaches infinity or x approaches negative infinity, I'm asking you for end behavior. What's happening on the left-hand side? What's happening on the right-hand side? If it's approaching a horizontal asymptote, then you'll actually get some number which we'll call L. So like I said, if the function does not approach a fixed number, then you look at the end behavior. It's either going to be positive or negative infinity. So don't be scared of this notation. All it's asking you about is end behavior. So suppose I ask you to find the limit as x approaches positive infinity. What did we just talk about? X approaches infinity, what side of the graph are you looking at? The right or the left? Right. So we're looking at the right. So the way this is read is this: the limit as x approaches infinity is L. If you have a horizontal asymptote. L is just your horizontal asymptote. If there's no horizontal asymptote, then you're looking at the direction that the graph is going. So you've been doing limits. You just haven't been seeing this notation before. So now notice if you're looking at the limit as x approaches negative infinity. So instead of looking at the right-hand side of the graph, what side of the graph am I going to look at? I'm going to look at the left. So the limit as x approaches negative infinity is L, which is a horizontal asymptote if you have one. Like I said, if there's no horizontal asymptote, it's just the end behavior. So let's look at some examples here. So you always have to visualize in your mind the end behavior. So for example, look at 2a. It's the same as the second. It's just one has positive and one has negative. So let's take a look at some examples here. So the limit as x approaches positive infinity. So what side of the graph am I looking at? Am I looking at the right or the left? The right. So now this is what you have to remember about an even degree polynomial function. It's an even degree polynomial function. What's happening with the leading coefficient? Is it positive or negative? Positive. So what's going to happen with my ends? Are they both going to go up, down, or different directions? Up. So they're both going to go up. So now again, just do a quick little sketch. All right? So now what's happening with the behavior is x approaching positive infinity. It's going to go, it's pointing up, so it's pointing towards what? Infinity. So there's your answer. So anytime they ask you for limits as x approaches positive or negative infinity, it's the end behavior. Or you can have an asymptote. Let's take a look at this one. Again, it's the same graph as A, but this time I'm asking you about negative infinity. So what side of the graph am I looking at, right or left? Left. So what would the limit as x approaches negative infinity for this one be? Infinity. So let's look at C. The limit as x approaches negative infinity. So what side of the graph am I looking at, right or left? Left. Now it's an odd degree polynomial function, but what's happening to my leading coefficient? My leading coefficient is negative. So remember, what's happening with an odd degree leading coefficient is negative. That's what the behavior looks like. You've got to remember what the behavior is. So on the left-hand side, what's happening with the direction of the graph? Is it pointing up or is it pointing down? Up. So it's going towards what? Infinity. So any questions on how you actually find the limit as x approaches positive or negative infinity? So now here's one where I gave you the graph. Look at the limit as x approaches positive infinity. Which end of the graph am I looking at? I'm looking at the right. So what's happening with the behavior? It's pointing towards where? Negative infinity. What's happening on the left-hand side? The left-hand side is also pointing towards what? It's also pointing towards negative infinity. Limit as x approaches infinity. I'm looking on the right-hand side, so what direction is this pointing on the right? It's pointing towards where? Negative infinity. X approaches negative infinity, it's pointing up, so it's pointing towards what? Positive infinity. So any questions about the limit notation? Like I said, the limit notation as x approaches positive or negative infinity, you're just looking at the end behavior. All right? So a couple more things about polynomials. So sketches. So we're going to sketch this graph. We've already done the factoring, find your intercepts, and then the limits as x approaches positive or negative infinity. So first of all, the intercepts are what? Your solutions. Remember, solutions are your x-intercepts. So let's talk about the x-intercepts for a minute. So it's already factored. How do you find your x-intercepts? You're simply going to do what? Take each factor and set it equal to what? 0. So if x minus 2 equals 0, one of your solutions will be at x equals what? 2. Now this is where you want to know what's happening graphically at 2. Is it crossing or is it touching? Look at the multiplicity. The multiplicity is even. So what's going to happen graphically at 2? It's not going to cross, but it's going to touch. So now look at x plus 1. Set it equal to 0. So what's another solution or x-intercept going to be? X equals what? Negative 1. So now what's going to happen, this one has an odd multiplicity of 3. So what's going to happen? It's going to cross. Now, I don't know if you remember this or how much it was emphasized last year. It is going to cross. I call it crossing with a kink. Anytime you have an odd multiplicity and that odd number is greater than 1, it's going to cross over with a kink. And I'll show you what I mean by that. It's just not going to look like a straight line crossing through that x-axis. It kind of has like, it looks like that cubic function, that x to the third, where it makes that little bit of a turn there. So that's what I mean, it crosses with a kink. It's just not crossing straight over. All right? Corby, can you put that one, please? You take your earbud out. Oh. The other one. Thank you. Put the phone away in your backpack. I don't want to see it again. So now let's take a look at x minus 1 equals 0. So what's another x-interceptor solution? X equals what? 1. Now what's the multiplicity for x minus 1? The x minus 1 has an odd multiplicity, correct? So what's going to happen? Is it going to cross or touch? Cross. And this one will just cross straight over because you have a multiplicity of 1. All right, so any questions about how you know whether it's going to touch or cross at those particular x-intercepts? All right, so now you need to know the degree of the polynomial. Because now we need to figure out what the n degree. The way you figure out the degree, if you remember from last year, you add all your multiplicities together. So what is the degree of this polynomial function going to be? So just add your multiplicities. You have 4 plus 3 plus what? 1. So it's going to be an 8th degree. Tell me about the leading coefficient. Is the leading coefficient positive or negative? Positive. So it's an 8th degree polynomial function with a positive leading coefficient. So then what's happening with the limit as x approaches positive infinity of f of x? So again, what's happening on the right-hand side of this graph? If it's an even degree polynomial function with a positive leading coefficient, it's going to be facing positive infinity. So then the limit as x approaches negative infinity of f of x is also going towards infinity. So what that means, remember, is both ends are going to be pointing up. That's what it means about finding the limit, using that limit notation. All right, so again, you've got to know the degree. You've got to know what the leading coefficient is in order to know what the end behavior is. Remember, if it's in factored form, you add up all your multiplicities to find the degree. So any questions on why this is an 8th degree leading coefficient with a positive leading coefficient? All right, so now let's start putting our graph together. So at x equals 2, we know it's going to touch. At x equals negative 1, it's going to cross with a kink. At x equals 1, it's just going to cross over. The only last piece of information we need to help give us a sketch is find the y-intercept. I don't care what kind of function I ask you to find a y-intercept for. How do you find y-intercepts? Of anything. Lines, whatever. What do you set equal to 0, x or y? X. So remember, to find any y-intercept, all I'm going to do is plug in 0 for x. So y is equal to 0 minus 2 to the 4th times 0 plus 1 to the 3rd times 0 minus 1. Well, it's 2 to the 4th. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this is 16 times 1 times negative 1. So what's the y-intercept going to be? 0 comma what? Negative 16. So again, just put a point way, way down here at negative 16. So now remember, at negative 1, it's going to cross with a kink. So what I mean by that kink is this. It's going to kind of do a little kink there at negative 1. Go down to negative 16. We know it has to cross over the y-axis at negative 16. It's going to come back up, cross over at 1. We have no idea how high this is going to be. So there's going to be variations in all of our graphs here. So we know it's going to have to go up and then come back down, touch it 2, and then go back up. So the variation in all of our sketches is going to be how high this point is right here. We don't know enough math yet in order to find that point. We need some calculus in order to find it, or your calculators. All right? but this is what I mean by kink. It's got that little kink to the curve in it. All right? Yes, Brian. It determines if you have a reflection or not. So if the leading coefficient is positive, both ends go up. If you had a negative sign in the front here, then both ends would go down. That's why you gotta know the degree and the leading coefficient in order to know what's happening on the ends. Yes. If the multiplicity is odd, and if it's not a 1 multiplicity. So if it was a 3rd, 5th, 7th, 9th, then it's gonna have a kink. The only one that'll cross straight over is if it's to the first, if that factor has a power of 1. Yes. You mean if it's a 9th degree?
Yeah.
Yeah, one side would go up and one side would go down. Right. Both ends would be the same way. So any questions on how you can sketch your polynomial? Yeah. You add your multiplicity. So you add all the factors together on the with the factors there. Yes, Emily. Yep, it balances off. Yep. So if this was a 4, 8, 12, as long as it's even, you know it's just going to touch. Okay. Any questions on that one? Let's take a look at another one. So again, very similar to what I did in the last problem. Determine whether find the zeros. Determine whether it crosses or touches. And this one's also asking for maximum number of turning points, then do a sketch. So first of all, let's start with the zeros. So give me a 0 for part A. X equals 4. What's another one? -2, and what's another one? 3. So now part B is asking to determine whether it crosses or touches. What's happening at 4? Is it going to cross or touch? Touch. Why is it going to touch? The power's even. The power's even. Okay. At -2, what's going to happen? It's going to do what? Cross. What's going to happen at 3? Cross with a key. There's technically a better name for it. It's called a inflection point, but you'll get to that later on in calculus. But again, it just crosses with a key. So are we good on A and B? C. So let's talk about maximum number of turning points. Well, first of all, you have to know the degree. So what is the degree of this particular polynomial function? The degree is what? 6. So it's a 6th degree, so maximum number of turning points is always 1 less. So the maximum number of turning points is going to be 5. So remember, there's a relationship between the degree and the maximum number of turning points. It's always 1 less than your degree. So now, what's happening with my leading coefficient in order to answer the next part? What's the limit as x approaches positive infinity and the limit as x approaches negative infinity? Well, what's happening with the ends? It's a 6th degree polynomial function where the leading coefficient is positive. What's happening with both ends? Both ends are doing what? Pointing up. So this is going to go to infinity. The limit as x approaches negative infinity will also go to infinity. Okay? And then for part E, let's do a sketch again. So at x equals 4, we're touching. X equals -2, we're crossing. And then x equals 3, we're crossing with a kink. The only last piece we have to do is find the y-intercept. Again, how do you find the y-intercept? You're going to plug in what for x? Plug in a 0. So again, 0 minus 4 squared, 0 plus 2, 0 minus 3 to the third. -4 squared is 16 times 2 times -27. But we know we're going to get a really small number down here, aren't we? So just put that point as low as you can on the y-axis. If you had a calculator, I'd expect you to, but I would expect you to work that one out. You just want to have an idea as to how far down it's going to cross the y-axis. If it's a reasonable number, I'd expect you to give it to me, but 16 times 2 times -27, we know it's going to be way off the graph anyway. And it's going to be on the negative side. So now, it's going to cross at -2. Remember, both ends are facing up. We're going to go down. At 3, remember, it's going to cross with a kink. And then at 4, it's just going to touch. Don't get stressed if you don't show that kink very well. Some of them are a little bit harder to get than others. All right, any questions on that one there? All right. So let's take a look at, so any questions, guys? We're going to go ahead and skip over Part B. Those don't have some pretty numbers, so let's not worry about Part B. So any questions given this information, answering any of those questions? So if you're comfortable doing a sketch, finding your multiplicity, crossing and touching. All right, so let's take a look at another variation of what you have to be able to do. This is where, notice I'm not giving you the function. I want you to write it yourself and then sketch. So I have a degree of 3. This P of 1 equals -4. This is just a point on the graph. The purpose of me giving you a point is because you're going to have to use that to help us find the leading coefficient. Because remember, in order to do a good sketch, I've got to know if that leading coefficient is positive or negative. All right, so I'm going to use this in a minute to help me calculate that leading coefficient. Now I'm giving you the zeros. So the 0 is -1 with a multiplicity of 2 and a 0 of 3. So what we want to do is start by putting this in factor form. I don't know what the leading coefficient is yet, so I'm going to call that A. If my 0 is -1, what factor did -1 come from? Put it in factor form. What factor did -1 come from? X plus 1. And because it's a multiplicity of 2, I've got to give this exponent of 2. If I have a 0 of 3, what factor did 3 come from? X minus 3. So remember, I'm only asking you to write this equation in factor form. Is everybody okay so far? The only last piece I have to do is I have to find the leading coefficient. That's where I have to use this point that they're giving me. Remember, 1 is what? The X or the Y value? X. -4 is the Y. So now what I'm going to do is I'm going to plug into what I have written so far, 1 for X, -4 for Y, and I'm going to solve for A. So I'm going to take -4, set it equal to A, times 1 plus 1 squared, times 1 minus 3. So -4 is equal to A, times 2 squared, times -2. So -4 is going to be equal to -8A. So what's A equal to? 1/2. So now you can actually write your entire function. So P of X is equal to 1/2 times X plus 1 to the second times X minus 3. There's your polynomial function. So like I said, the only purpose of that point is you have to use that once you put it in factor form to find the leading coefficient. So just like I did in the last 2 examples, yes, Emily? Yes. Yeah, you don't have to multiply that. So -1 has a multiplicity of 2. So what does that mean graphically at -2? What's going to happen at -1? Is it going to cross or touch? Touch. What's going to happen at 3? It's going to do what? Cross. Does it cross with a kink? No. So the only last piece that's missing to help me come up with a sketch is what? What else do I also need to know? Y-intercept. How do I find the y-intercept again? 0 in for X. So I have 1/2 times 1 times -3. So what's the y-intercept going to be? Y would be what? 0, -3/2, or 0, -1/2. Make sure you're labeling your X and Y axis. So any questions about how I put the X and Y intercepts on the graph? Now, the only other thing we need to talk about is the end behavior. So it's an odd degree polynomial function. Look at your leading coefficient. The leading coefficient is what? Positive. So again, an odd degree leading coefficient is positive. It's going to have this general shape like that. So the left side's pointing down towards negative infinity, the right side's going to be going up. Like I said, you got to know what those end behaviors are. Okay? So remember, at -1, it's going to touch. So it's going to come from negative infinity, touch at -1, it'll go down, cross over the y-axis at -1.5, and then remember at 3, it's just going to cross over. So there's a sketch of that polynomial function. So any questions on example 5? Okay, because if this had a multiplicity of 1, if it had any other multiplicity, it would be, they would let you know. So if any time it's a multiplicity of 1, it's when it crosses straight over. It's only if it had if the multiplicity was greater than 1. If greater than 1 and it's an odd power. Okay. So if this was a multiplicity of 3, 5, 7, 9, etc., then you cross it. Okay. So any questions on example 5? Let's take a look at the next one. So again, degree of 4, p of -3 is -6. We have a 0 of 1 with a multiplicity of 2, -2 with a multiplicity of 2. So first of all, to write your polynomial function, again, we're going to have to find the leading coefficient in a minute. Find a 0 of 1. What factor did 1 come from? 1 came from a factor of what? X minus 1. And what am I going to do? Take x minus 1 and raise it to what power? 2. Multiplicity of 2, when I have a -2, what factor did -2 come from? X plus 2. Remember, it's a degree of 4. After you write this in factor form, make sure all your exponents add up to give you 4. Okay? So we good so far? Now we're going to use this point to help us calculate our leading coefficient. So x is -3, y is -6. So -6 is equal to a times -3 minus 1 squared times -3 plus 2 squared. So -3 minus 1 is -4. -4 squared is 16. And then -1 squared is just the 1. So what's that leading coefficient going to be equal to? A will be equal to what? -6 over 16, and I can reduce that to -3 over 8. What is well, it's not left or right. What is -3? -3 is the x. -6 is the y. So again, that's why I put -6 on the left and -3 on the right. Okay? Because remember what -3 is, -6 represents. Okay, so everybody okay where I got the leading coefficient from? So then p of x, you can finish writing your equation, -3/8 times x minus 1 squared times x plus 2 squared. So now it's a 4th degree polynomial. Tell me about the leading coefficient. Is the leading coefficient positive or negative? Negative. So what does that mean? Are both ends opening up or are both ends going down? Going down. So I now know what the end behavior is going to look like. So tell me about what's happening at the x-intercept. What's happening at 1? Is it going to cross or is it going to touch? Touch. What's happening at -2? Is it going to cross or is it going to touch? Touch. So I know at 1 it's going to touch. At -2 it's going to touch. What's the last piece I need in order to help me come up with the sketch? Y-intercept. So y is going to be equal to, again, plug in 0 for x, -3/8 times 0 minus 1 squared times 0 plus 2 squared. So I have -3/8 times 1 times 2 squared, which is 4. So where is this y-intercept going to end up? It's going to end up at -3 over what? 2. Any questions about my points? So again, I know what's happening with my end behavior. I'm coming from -infinity, just going to touch the x-axis at -2. I'm going to have to then come down, cross over the y-axis, touch again, and then point down. So there's my sketch of the polynomial. All right, questions on it. You guys go ahead and try C for me on your own, and then we're done.